Good morning. Welcome to the fourth day of our Australia Brazil meeting. It's a pleasure to introduce to Professor Pinhas Grossmann, who speaks about modular tensor categories and subfactors.
Thank you. So first of all, I'd like to thank the organizers for organizing this wonderful conference and for inviting me. It's a great pleasure to be back here at IMPA, and I'm more generally excited about this idea of having Australian and Brazilian interaction. The title of this talk is Modular Tensor Categories and Subfactors. This does not have anything to do with string geometries and dualities, as far as I know. There'll be some talks today, I understand, about conformal field theory. This talk is tangentially related to conformal field theory in the sense that these objects, modular tensor categories, arise in conformal field theory, in fact, originated in conformal field theory. But this is essentially going to be an algebraic talk. Because the talk is a bit off topic, also, it's not going to be technical at all. So it'll be more of an overview talk. I just want to explain what the two words in the title are, especially the first one, and a little bit about their relation, and discuss some general questions in the field as it stands now. And the talk will be more about the first word than the second. So actually, I'm more from subfactors, the second word. I've been getting interested in modular tensor categories more recently, so I'm a bit new to this myself. But I think they're very interesting, and I'll talk about them today. So here's a brief outline of the talk. I'm going to give some very brief motivation without really saying anything specific about why people have been interested in modular tensor categories, which are actually not the reasons I'm interested in them, but the origin of them. Then I'll spend a bit of time explaining what a modular tensor category is. Then where do they come from? So what are the sources of examples of modular tensor categories? Then I'll discuss briefly the relationship between modular tensor categories and subfactors. I'll say what a subfactor is and indicate the relationship here. And finally, end with some general questions and conjectures in the field. OK. So modular tensor categories are algebraic structures. They're categories, but they're really, in fact, finite algebraic structures. So think of a finite group or a finite ring. They're a bit more complicated because they're categories, they're morphisms. But they're essentially finite algebraic structures. They've come up in a number of places. So the origin of modular tensor categories is conformal field theory. So Moore and Seiberg discovered a bunch of very interesting properties of conformal field theories. They didn't use the word modular tensor category. These were later realized to be the properties they were describing were essentially the properties of a modular tensor category. A formal theorem proved more recently by Huang is that certain types of vertex operator algebras give you modular tensor categories when you look at the category of representations. So they're categories of representations of conformal field theories. So that's the origin of modular tensor categories, I guess. Second large source of interest to mathematicians in modular tensor categories was the work of Witten and later Reimundo and Turayev, who constructed invariants of knots and links and three manifolds and topological quantum field theories where the input is the modular tensor category. So from a modular tensor category, you get some sort of three-dimensional TQFT and invariants of three manifolds and knots and links. And yet a more recent application is a number of mathematicians and physicists working on quantum computation have a theoretical model for quantum computation, which is based, again, takes as an input modular tensor category. So the modular tensor category gives you some data that you use to describe a theory of quantum computation. So this is Friedman, Kitaev, Wang, and others. There's an outpost run by Microsoft in Santa Barbara, Station Q, where they work heavily on this approach. This is all very general, and I'm actually not going to say anything at all about this for many reasons, one of which is I don't know that much about any of these things. None of these are my fields. But these are the main reasons that people have been interested in modular tensor categories. OK, so with that out of the way, let me talk a bit about what a modular tensor category is. OK, so what looks like a group but is not a group? So it's a philosophical question. So there are many answers to this. Quantum group is of course, a good answer. And our answer is going to be very similar to quantum group. Modular tensor categories are closely related, in fact, to quantum groups. So it's a very old and useful idea in mathematics is sometimes you're thinking about some well-known object, if you abstract the properties, you write them down, and you notice some of them are maybe more or less, maybe not as essential as you might have thought, and you ask what happens if you remove one property, and this has led to many great discoveries in mathematics. So famously, there's the non-Euclidean geometry if you drop the parallel postulate. Another famous one is if you look at the algebra of functions, let's say on a compact Hausdorff space, and you write down what properties does the algebra of functions in a compact Hausdorff space have, and you write them all down, then you throw away the fact that multiplication of functions is commutative, then you get the notion of a C-star algebra. I guess in the compact case, a unital C-star algebra. And this idea, of course, underlies a large area of mathematics, non-commutative geometry. You look at non-commutative analogs of function algebras. And more generally, dropping commutativity is, I guess, a key idea in many of the areas of mathematics that are broadly inspired by quantum mechanics and related physical discoveries and theories. So the reason, this is all not really saying anything, but the reason I mention this is because I think that the best way to think of a modular tensor category is going to be as a non-commutative analog of a finite group. And you may be thinking that finite groups are already allowed to be non-commutative, so this is not really a new thing. But it depends on how you think of commutativity. So from a representation theoretic point of view, all finite groups, even non-commutative finite groups, are in fact very commutative from a representation theory point of view. So that's I think, the best way to think about what a modular tensor category is. So let's review a bit, again, without really any details, representation theory of finite groups. So you have a finite group. You look at the category of representations on finite-dimensional vector spaces. Let's just take the field of complex numbers. So you have a category. The objects are representations. The morphisms are linear maps that intertwine the action. Then you get so it's a linear abelian category. There are finitely many simple objects. So there are finitely many irreducible. So simple object here would be an irreducible representation. And as long as you're working over the complex numbers, certainly, this is a semi-simple category. So every irreducible representation of a finite group over the complex numbers will decompose as a direct sum of irreducible representations. OK. So there are many other properties that this category enjoys. So first of all, it's a monoidal category. So you can take a tensor product. In category theory, you don't really want things to happen on the nodes. You want things to happen up to some sort of notion of natural isomorphism. So the tensor product is associative up to some associativity isomorphisms satisfying these pentagon equations. It's called the associativity constraint. There's a unit, so the trivial representation functions as a tensor identity. So tensoring representation with the trivial gives you the same representation back. And again, you should have isomorphisms, natural isomorphisms realizing this unit. So it's a monoidal category. It's rigid and spherical. So I'll briefly say a word about what this means here. So roughly, rigid means the objects have duals. So representation, if you have a representation of a group on a finite-dimensional vector space, you can represent it on the dual vector space as well. And there are evaluation and co-evaluation maps satisfying relations. These are best thought of pictorially. So there's a well-known graphical calculus for tensor categories. Here, we ignore all the, we assume, let's say, it's a so-called strict category. So we ignore all the associativity maps. So basically, you have morphisms, elements of some Hom space are represented by a box with strings coming out. So I draw things from top to bottom. So the strings coming out indicate what the objects that, the source and targets of these morphisms. So this is a morphism from X to Y tensor Z. Then composition is just vertical concatenation. If you have T from X to Y and S from Y to Z, you just draw them on top of each other, and that gives you a map from X to Z. Tensor product is just done by horizontal concatenation. So if you have a map from X to Y and a map from Z to W, you just draw them next to each other, and that gives you the tensor product map from X tensor Z to Y tensor W. And there are a couple of special morphisms. So every object has an identity morphism. So that's just drawn by a straight line from X to itself. And then you have these evaluation and co-evaluation maps. So if X has, so a dual object means there should be an object X star. Then there should be two maps. So you have a map from X tensor X star to the identity. This is drawn, we sort of suppress the identity in the box, so it's just drawn X to X star. And then another map from X star, from the identity to X star tensor X. And the zigzag relations they're supposed to satisfy are if you have, so you look at evaluation map, you can draw, so here's the evaluation map, here's the co-evaluation map. You can fill in your picture with identity morphisms, and what you want is that this should be the identity morphism on X. So here you have, these are, of course, these are, again, using this notation, these are tensor products, and this is composition. So you get the zigzag. And you should have the other zigzag as well. So you can do it the other way. You can do, what is the other way? X to X star. I feel like I'm going to do the same one again. No, okay. So this should be the, identity morphism on X star. So rigidity means that for every object X, there should exist such an object X star together with a pair of maps like this, such that these relations hold. I always never know which is right duality or left. I was trying to write down left duality, but I just looked it up before the talk. This is right duality. So there's the opposite version of left duality. We want them to both be true. So every object should have a left and right dual. It turns out this dual object X star is unique up to isomorphism, including with these with the duality maps. Everything is unique up to unique isomorphism, in fact. Right. So rigidity means that this graphical calculus is much more power because you can sort of wiggle strings around, loop strings over each other, always taking a dual object and just moving strings like that. So it gives you much more power in drawing pictures. So that's a rigid monoidal category. Sphericality is the following. So sphericality gives you a nice notion of trace. So you have some object, X, so you can look at, or some morphism rather. So let's say this is a morphism from an endomorphism of X. So you want to take the trace. So let me do it the right way. So you can try something like this. You can take this is the co-evaluation map. So you go from the identity to X star tensor X. Now you'd like to close this off to get a closed picture. So you want to have an X star here, and you can draw an identity morphism. The problem is this should be an evaluation. But here, you don't actually have X. What you have is X double. This should be an evaluation map of X star. So it should go from X star, tensor X star star to the identity. So if you want this picture to make sense, you need some way of, something linking X to X double star. So a natural isomorphism linking X to X double star is actually called a pivotal structure. Spherical means a pivotal structure such that there's also, you can also do this picture the other way. So a spherical structure is a natural monoidal isomorphism from X to its double dual, such that these two pictures are the same for all endomorphisms too. So that's called a spherical category. What's that? Yeah.
So this natural isomorphism from this double star is trivial.
Yeah. In this case, it's just trivial. It's just the normal way you identify a representation with this double dual. But in fact, I think it's conjectured. So I'm going to write down a couple more axioms. This is going to be what we call a fusion category, the generalization of a rep G. It's conjectured that every such category admits at least a pivotal structure, maybe even a spherical structure, but I think it's unknown. So it's open whether all these categories I'm going to discuss automatically admit such a thing. But certainly for the well-known examples like rep G, it's always there. Yeah. Okay. The next property to mention is symmetry. So there are natural isomorphisms from X tensor Y to Y tensor X. For a tensor product of group representation, this just means flipping the order of the two vector spaces. And these satisfy braiding. So again, there's a pictorial way of doing this. So you draw the braiding as a map from X tensor Y to Y tensor X. Then naturality means that if you have some morphism from Y to Z, and you apply the morphism and then braid X with Z, this should be the same as first braiding X with Y and then applying the morphism. And the same thing on the other side. So this is naturality. And the so-called hexagon relations means that if you have a tensor product, so you braid X with Y tensor Z, this should be the same as first braiding X with Y, and then braiding with Z. This is X here. So doing it in one step or two steps is the same. It's called a hexagon because when you put in all the there are associator maps. If you put in all the associators, then you have to draw a hexagonal commutative diagram. It's called, this is not a symmetry. This is what we call a braiding. There's a braiding. I want to erase that. So symmetry is one more. This is called a braiding because if you have such a thing, you get a representation of the braid group on tensor powers of objects. And symmetry means that the braiding is essentially trivial. So if you braid X with Y, and then you braid Y back with X, then you just get the identity. So this is symmetry. So this is sort of the maximal commutative. So braiding is already a form of commutativity, but symmetry is sort of the maximal form of commutativity in a monoidal category. So rep G is symmetric. And finally, this is sort of an optional property. You can also look at the category of unitary representations, and that's monoidally equivalent for finite groups. That's monoidally equivalent to the category of ordinary representations. The unitary, though, has a lot more structure because you can take adjoint. You have an inner product, you can take adjoints of maps. So there's more structure, but you get the same underlying monoidal category in the case of a finite group. OK, so that's a lot of properties. So what do we want out of all this? So a fusion category is simply a category. So a fusion category should be thought of as a generalization of rep G. So a fusion category, it's a linear, semi-simple, rigid monoidal category with finitely many simple objects and simple identity object. So we want basically everything from the previous slide, except we generally do not require explicitly sphericality or braiding. So we don't require any braiding, and we don't require sphericality. Besides that, we basically want everything that a group has. This is called a fusion category. And this definition in this form is due to Ettinghoff, Nikšić, and Ostrich have studied this have been the ones who pioneered the study of these kind of categories. So it's basically, it's basically meant to be some sort of generalization of rep G. So for finite group G, rep G is a fusion category. And there's a sort of converse, which is that if you require your fusion category to be symmetric, then every symmetric fusion category actually is monoidally equivalent to rep G. There's one caveat, which is that you need a little more than the group. You can also have Z2 grading. So you want to so you can look at supergroups. So a group with an involution in the center, and then the representation category has a Z2 grading, and there's a way to twist the braiding by that grading. So if your group has a central involution, then you might have multiple different symmetric structures. But besides that little side point, a symmetric fusion category is always of the form rep G, possibly with some additional structure coming from a Z2 grading. So a symmetric fusion category then, from a representation theory point of view, a symmetric fusion category basically is a finite group. It's a representation of a finite group, really a finite supergroup. So this comes from a theorem of Deligne, which is much more general. So Deligne's theorem is not just for finite categories, it's a much more general thing, which I don't know too much about. OK. So then you can ask, so fusion categories don't have to be symmetric. They don't even have to have braiding at all. So what occurs in the non-symmetric case? So here's the definition of a braiding. I'm not going to so this is sort of what I wrote down before. So the braiding is this thing, except we don't require the braiding to be trivial, right? So a braiding is a way of a commutativity of objects in your category. And this is due to Joyal and Street. And then you can ask, given a braiding, how close or how far is the braiding from being symmetric? How trivial is the braiding? So that's the natural thing to wonder. And so one way to look at it is through this notion of a Muger center. So given a braiding, you can ask, for which objects X is it true that braiding with every other object Y gives you something trivial. So which object, this is in some sense the center of, so a braided category is sometimes viewed as already being commutative, but this is an even more commutative version, right? So this is the like sort of a second order center. Which objects braid trivially with everything else in the category? This will be a tensor subcategory of your original category. It'll be in fact a symmetric tensor subcategory of your original category. So what this means is that if your category is already symmetric, that means it's equal to its Muger center. Everything braids trivially with everything else. Then you might have braidings where the Muger center is some proper subcategory. A modular tensor category, so this is not the most classical definition, but a modular tensor category just simply means a braided fusion category, like a braided spherical fusion category, where the Muger center is trivial. So nothing braids trivially with everything else. Everything has some non-trivial braiding. So again, I think the point of view here should be that a modular tensor category is a maximally non-commutative analog of a finite group. A finite group is like a symmetric fusion category, and a modular tensor category just means it has a braiding, so it's somewhat commutative, but the braiding is non-trivial for every object. So it's a very non-commutative braiding. So this is the definition of a modular tensor category. Non-co-commutative. I don't know. Yeah, I don't know. I guess maybe, yeah. Maybe that would be better. Okay. So modular tensor categories, as I mentioned, came up originally in conformal field theory in the work of Moore and Seiberg. So they have a lot of structure. So you can define so-called S and T matrices. So the S and T matrices come from the braiding. You can try to define S and T matrices for any finite braided category. So, well, any braided fusion category at least. So, spherical fusion category. So you take a braiding of two objects, and then you do it again. So if this was symmetric, you'd just be getting the identity. But in general, these are modular. The one case we're interested in is the modular case. And then you take the trace. So we're in a spherical situation, so you take the trace on both sides. So you have, and I'm almost certainly going to draw this wrong, because I always do. I guess I need a hole here. You get some sort of, is that right? Yeah. It's just a link, two circles linked together. I don't know why that's so hard for me to draw, but yeah. Okay. Labeled by two objects. So for any, so this will be some scalar. It'll be some. It's an endomorphism of. So it's a map from the identity to itself. So it's a scalar in your field, which is the complex numbers. This is just some complex number associated to any two simple objects in your category. So you get a square matrix where the rows and columns are labeled by simple objects. And for every two objects, you have this link, which gives you a number. This is called the S matrix. So this is S, X, Y. And then you have a T matrix. So the T matrix is going to be diagonal, so you just define it for each simple object X. And for this one, you take the braiding, and you just take the trace on one side. So so they call it a twist. So this is a map from X to itself. And again, since X is simple, this is a scalar multiple of the identity morphism. These are the S and T matrices. So it turns out they're automatically unitary matrices. You get a projective representation of SL2Z, and particularly get an actual representation of PSL2Z. So you get a representation of, I guess the modular group is usually a PSL2Z, but so you get a projective representation of SL2Z or an actual representation of PSL2Z. And a really amazing property is summed up in the Verlinde formula, which is that the tensor product decomposition rules of your category are completely determined by this S matrix. You can read off these are integers. So a priori, these numbers are not integers. These are some complex numbers in some number field. But when you take these sums, you get integers, non-negative integers, and these integers give you the structure constants for decomposing tensor products of simple objects. This is a really, really amazing fact, again, discovered in conformal field theory, and I think shows how much structure these modular tensor categories have. Okay. So that's the second. That was the second part of the talk. What are modular tensor categories? So now let me talk a little bit about what are the sources of examples of modular tensor categories. So where do they come from? So one source is quantum groups. So if you have representations of you have quantum groups which come from, there are many different constructions, but in some sense deformations of Lie groups. There usually is a parameter associated to these deformations. If you take the parameter to be a root of unity, then you can get modular tensor categories. In general, these representation categories are not semi-simple, but there's a construction to pass towards semi-simple categories, and these give you modular tensor categories. So I'm not going to say anything really else about this, but this is a major area of study, quantum groups and their representations. And again, at roots of unity, you'll get, so you have to maybe be a little careful about which quantum groups and which roots of unity, but certainly for many of the compact Lie groups at roots of unity, you'll get modular tensor categories. A second source of examples is through a construction called the Drinfeld center. So if you have a monoidal category, you can look at, so let's say you don't have a general braiding in your category. It might be that some particular objects can be braided with all other objects in the category. So given a monoidal category, you can look at the subcategory of objects that can be braided, and a given object may admit braidings in several different ways. So the objects of the Drinfeld center are going to be pairs, which consist of an object in your original category together with a way of braiding it with every other object in your category. It turns out this Drinfeld center, is itself a monoidal category. The Drinfeld center is braided because it was constructed as objects with braiding. So the Drinfeld center automatically has a nice braiding. And this is something that's, I think, very non-obvious, but true, that if you start off with any spherical fusion category with no braiding at all, and you look at the Drinfeld center, that will be a modular tensor category. This is something very non-trivial. There's no real reason why you would expect to get a nice S&T matrix just from some arbitrary spherical fusion category, but it's true. And this is, I should say one more thing, which is that how big is the Drinfeld center? So it's not obvious there should really be anything in the Drinfeld center. Well, it should be the identity. You should have the unit should braid trivially with everything. So you should have an identity. But maybe there's actually nothing else in the Drinfeld center. But in fact, for a spherical fusion category, the Drinfeld center is always larger in some sense than the original category. So these categories have a notion of dimension, and for a finite group, the dimension is just the order of the group. The dimension of the Drinfeld center as a category is always the square of that. So it's a little bit counterintuitive. You think of taking the center as some subcategory, but because you have different ways of braiding the objects, something that's, for example, not simple in the original category may be simple as a, so you end up with something much bigger, and in fact, the dimension is always predictable. It's always a square of it's always sort of a square as big as what you started with. So it's a sort of, I think, amazing thing, but it's true. Okay, so, and here's another interesting fact, which is, I guess, not a result, but just sort of an observation, which is that there's every known example of modular tensor category essentially comes from these two constructions. So there are no known examples of modular tensor. I guess you can take tensor products of these two things, or maybe some slight modifications, but there are no known examples of modular tensor categories that are not sourced in either quantum groups or Drinfeld centers. So this is really the only known way to get a modular tensor category at this point in time. I mentioned in the beginning that they'd rise as representations of VOAs, but as far as I know, the only representations of VOAs that are known are either come from quantum groups or are Drinfeld centers or something. So there are no other examples, as far as I know, of modular tensor categories. Okay, so it's a pretty small world so far. So we have these two methods, and in the rest of the talk, I'm going to focus on the second one, because quantum groups is sort of its own area, which I'm not actually an expert in. And the one that's more relevant to subfactor theory, which is what I want to talk about a little bit, is these Drinfeld centers. So the Drinfeld center, again, you start with some ordinary fusion category, maybe without any braiding, you pass to the Drin center, and that gives you a modular category. Yes, there's an overlap. So the Drin center of something could come from a quantum group. There are, so there are definitely things in one that are not in two. So there are certain, so being the center of something gives you some extra properties. So certainly some representation categories of quantum groups are known not to be centers of anything. And the second one is a bit harder to say with definitively there's something in two which is not in one, because given the Drin center of something, you have to know there's no quantum group at any level. And that can be hard to tell. So I'm not sure if that's known for sure, but I don't think there's any reason I think probably there should be things in two that are not in one as well. But definitely there's an intersection. Yeah, there's definitely an overlap. OK. And I'll say something in the end. There's some conjecture about these two constructions generating modular tensor categories in a suitable sense. So I'll mention at the end there's some conjecture that these two constructions should generate. But that's just a conjecture at this point. All right. So as we've seen, all modular tensor category, well, the known examples come from either quantum groups or Drin centers. So the next step is if you want to know what you get as Drin centers, you have to go back a step and ask, what are the fusion categories? If you want to get centers, you should ask, what are the things that you're going to take centers of? And here, there's also a few basic constructions. So again, quantum groups give you fusion categories. If you take groups that aren't quantum groups, like an ordinary finite group, you'll get a fusion category which will not be modular. It'll be symmetric. So that's that will be a fusion category which is not modular. Another construction is subfactors. So let me say, that was the other word in my title. So let me say what a subfactor is. So there's notion of a Neumann algebra. So it's a star algebra of operators on a Hilbert space, which is the commutant of a unitary group representation. So that's the von Neumann algebra. This is equivalent to saying it's closed in certain topologies. Then you can look at those von Neumann algebras which have trivial center. So these are the most basic building blocks of von Neumann algebras. And a subfactor is basically just an inclusion. Well, it is just an inclusion of two factors. You want to have you want to eliminate certain types of factors. So you don't want to look at finite dimensional matrix algebras, but essentially a subfactor is an inclusion of two von Neumann algebras, two factors. OK. So these give you fusion categories in some cases, and let me explain briefly how that works. So suppose you have a subfactor, and again, if you don't know anything about von Neumann algebras, it's not really important here. These are just an inclusion of two algebras or two rings of a special type. Then there's a notion of index. So the index is supposed to generalize the index of a subgroup in a group, and it's supposed to correspond roughly to how big the larger algebra M is as a module over the smaller algebra. So it's a dimension of M as a module over N. So this notion of dimension goes back to Maria von Neumann in the early 20th century. And a famous theorem of Jones from the early 80s says that this index is not necessarily an integer, but below the number 4, there's only a discrete set of values that the index can take. Above 4, it can take any value, and below 4, it can take this discrete sequence of values. Now, given a subfactor with finite index, the index may be infinite if your subfactor is very small inside the larger algebra, but if you have a finite index subfactor, you can look at the category of NN bimodules, which is tensor generated by the full algebra, and this gives you a nice tensor category. So you get a semi-simple rigid monoidal category. In general, such a category is not unnecessarily finite. So there can be infinitely many different simple objects. Even if the index is finite, there's no reason that the resulting category should be finite. However, in some cases, it turns out to be finite, and then what you get is, in fact, a fusion category. And this construction is actually universal. So every unitary fusion category, so you need to put unitary in there if you want to get it from operator algebras, but any unitary fusion category can be realized from subfactors. So subfactors gives you a universal construction for unitary fusion categories. So if you want modular tensor categories, the idea is you can try to find subfactors, you get some unitary fusion category, you pass to the Drin center, and that should be a modular tensor category. So that's the basic idea. Okay, maybe I should stop for a minute. Are there any questions?
There is a problem with classification of conformal theories. This gives new way of looking at that.
So again, something I mentioned at the end, this is sort of a big open question, is it's hoped that there are examples of fusion categories that come from subfactors which had not been noticed in conformal field theory. So that's sort of what I'll talk about next, and that's sort of the main point of this. However, we can construct some modular tensor categories which have not been seen in conformal field theory. Then the next question is, given such a new modular tensor category, is there some conformal field theory VOA which realizes it? And for these specific examples, the new examples we have, this is unknown. And more generally, there are those who conjecture that this should be true in general, that modular tensor categories should always come from VOA. But again, this is completely unknown, that no one really knows. But the hope is, or the thought or the hope is that maybe we get new examples, and then you can get new conformal field theories. The other point is that the new examples I'll talk about a bit later. So they were discovered through the classification of subfactors, but it's not really clear that, but essentially these are finite algebraic objects. So if you had the right combinatorial machinery, you could construct them without operator algebras. So it's not really clear that you need to really go through subfactors for this. Historically, these were discovered through the study of classifying subfactors. Anyway.
What is special about 4 being
So it's a good question. So this is not directly going to answer your question, but one thing is that below 4, if the subfactor gives you a finite category, you get an associated graph. Below 4, you always get Dickin diagrams of ADE, and the norms of these graphs squared as the index. So the ADE graphs are, in fact, I think the only bipartite graphs that have norms less than 2. So you get, so if you knew all the graphs were finite, this would be sort of a quick proof of part of Jones's theorem that the index has to be the norm squared of a graph, a bipartite graph. The only ones below 2 are the Dickin diagrams, simply like Dickin diagrams, and therefore the norms of those graphs are the 2 cosine pi over k. So above 4, you have more graphs. It doesn't completely answer your question because even above 4, the graphs are not going to give you a continuous spectrum. They're still only going to give you a discrete spectrum. But above 4, there are certain constructions that you need a certain amount of room to do. And basically, if the index is below 4, you don't have enough room to. So I mean, in Jones' original paper, he has an explicit construction of subfactors for all indices. And that construction just requires a certain amount of space. An index below 4 doesn't give you. That's not a very good answer, but yeah. Below 4 is just it's very tight, and you don't have enough room to do much. OK. So with index less than 4, you get these, as I just mentioned, you get these Dickin diagrams. All the fusion categories, in that case, are known from quantum groups. These are related to SU2, in fact, at different levels. So you get these quantum group categories. So it was natural to wonder what happens when you start looking at index slightly bigger than 4. You have maybe more stuff. But in fact, not that much new stuff was discovered slightly above 4. So there's a classification program to look at subfactors at these small indices. In the 1990s, they discovered a couple of them. So these 2 subfactors with these kind of weird numbers related to the square root of 13 and the square root of 17, known as Hagerup subfactor and the Aseda Hagerup subfactor. And they wrote this paper. I put the word exotic in quotes there. Exotic appeared in the title of the paper. The paper was called Exotic Subfactors with Index 5 plus square root of 13 over 2 and 5 plus square root of 17 over 2. The word exotic here was in the sense that these were the first examples of something coming from subfactors which was not already known from groups or quantum groups. This was the first new thing that appeared. And it was a bit mysterious. People were wondering, what are these things? Where do they come from? Why are they appearing? Are there many more of them, et cetera? This was a bit of a mystery in the 1990s. More recently, there's another one. This other one was sort of conjectured by Hagerup, but not constructed, and it was constructed by Bigelow, Morrison, Peters, and Snyder. This one has a slightly different, more complicated index. Index lies in a cubic field, so there's no nice quadratic expression for the index. OK. So small index is one way of trying to classify subfactors or fusion categories. There's another approach you can take to try to look at what are the simplest examples, and that relates to sort of how complicated the structure of the category is. So if you have a fusion category, you can look at the subcategory of invertible objects. And when I gave this talk in Australia, David pointed out to me that in conformal field theory, these are known as simple current extensions. These are just objects in your category such that there's something else you can tensor with to get the identity. In operator algebras, this corresponds to automorphisms as opposed to endomorphisms. So you can look at the subcategory of invertible objects. And if you forget about the category, you just get a finite group. So the simplest situation is when all the simple objects in your category are invertible. And in this case, you're basically just dealing with a finite group. There's really nothing else going on. This is called a pointed category. And a pointed category is just equivalent to graded vector spaces over a finite group. There's one subtlety, which is you have to write down some associator map, and the associator map brings in some cohomology. So there's a three cohomology class to deal with. But besides that, if all the objects in your category are invertible, then you're just in a situation of a finite group. So the next step up is what's called a quadratic category. A quadratic category means that you have invertible objects, and you have one other type of object. So you have the invertible objects act by tensor product, and they, let's say on the left, to make it easier. And a quadratic category means that you have only two orbits under this action of the group-like objects. You basically only have one kind of non-group-like object. So this is sort of the next simplest situation to a group-like category. You have group-like objects and one other type of object. So a motivating example of this is the Hagrob subfactor. So I'm not going to say much about the structure here, but as a ring, it's very simple. So the ring has, you're looking at the group Z3. So you have a ring it's a base ring. There are 6 base elements. So there's 3 group-like elements and 3 non-group-like elements. And the multiplication rules are very simple. The group-like elements multiply by the group rule. If you pick some non-invertible object x, gx is xg inverse, and then x squared is just 1 plus the sum of the non-invertibles. So it's a very simple ring. It's not clear why this is a category, but as a ring, it's extremely simple. You can get the index just by, so there's a dimension of objects, so you can get, the dimension is supposed to be some kind of, it's supposed to be a ring homomorphism, so you can get something like, you get some equation like d squared equals 1 plus 3d. So here d is the dimension of x, and then the index is actually just 1 plus d. So this is where this number 5 plus the square root of 13 comes from. It just comes from the ring structure. So I'm not going to explain more about this, but that's what the index is. So this is an example of a quadratic category. This group-like stuff, and you have this one kind of non-group-like thing. Okay. And again, it's not really clear why such a ring should have any categorical structure. And it could be that this ring has multiple categorical structures. In fact, it does have more than one structure as a tensor category. There is more than one so-called categorification. Okay.
Sorry, is
yeah.
This fusion category a modular tensor category?
No, it's not. So this one, in fact, even for Z3, here the fusion rules are actually not commutative, so it's not a commutative ring. So in this case, it's not going to have any sort of braiding whatsoever. It's guaranteed not to have a braiding. So for something, a braiding is a categorical way of commuting two objects, but if they don't even commute as a ring, then there's no hope of having a braiding. So this is a non-braided category. But again, it will have a Drinfeld center, so the Drinfeld center will be modular. Okay. So this category is called an Azumi-Hagrob category. This kind of category with this kind of ring is called an Azumi-Hagrob category. So you can replace Z3 by any other group, and you get any other, let's say, abelian group certainly, and you get some ring. If there's a category whose fusion rules are given by that ring, then that's called an Azumi-Hagrob category. So one obvious question is, so I just asserted, again, without any explaining why, that for Z3 there is a subfactor which gives you this ring. If you replace Z3 by some other group, is there a category which gives this corresponding type of ring? So that's a very basic question, and the answer is that we really have no idea. We know for some small examples, but we don't know in general. Okay. So in the 1990s, Izumi came up with this general method for constructing these kind of quadratic categories from endomorphisms of C-star algebras. So the construction problem is very difficult. If the category is group-like, then essentially you're just dealing with just a group. Then we sort of understand why it exists. It's in terms of operator algebras, it's just automorphisms. A group acting on an operator algebra. It's very simple idea. In this kind of ring, it's unclear what this object X is supposed to represent, right? You have the group-like stuff, and then you have this other thing, and what is the other thing? Why does it exist, and where does it come from? In operator algebras, basically the group-like things are supposed to be automorphisms. The X should be some kind of endomorphism with a proper image. You have to construct this endomorphism. So Izumi came up with a way of trying to figure out if there was such an X acting on an operator algebra, what would it have to look like? And he did some very intensive calculations, and he came up with this general method for figuring out what kind of endomorphism would give you this kind of ring structure. So he worked with these Kunst C-star algebras. He came with the classification, in fact, of these categories by polynomial equations, which are associated to these operator algebras. His method gives you a very explicit description of the categories, but you have to solve his equations. He solved these equations. So for Z3, you get this Hagrob subfactor. He solved them for Z5. And then his method is to give you such an explicit description that he actually computed the modular data, the S&T matrices, for the Drinfeld center. So that's very non-trivial. Even if you have a fusion category, the Drinfeld center is this very abstract construction. You look at these half braidings. It's very hard to compute in general. But Izumi's method is very concrete and explicit, and he computed the Drinfeld centers. So his method essentially gives a classification of these categories by solving polynomial equations, but the equations themselves are very, very hard to solve. So we solved them for Z3 and Z5, then he wrote down the general form of the equations, but didn't give any hint on how to actually solve the equations in general. So if you can solve the equations, you get categories, but we only know that he only solved them for Z3 and Z5. Some more progress was made by Evans and Gannon. So they looked at groups of odd order. They looked at cyclic groups. They solved them for 7, so 2m plus 1, so 7 and 9. They found some numerical evidence for a bunch more. So up to Z19, they seem to exist. For odd cyclic groups, up to Z19, the categories do seem to exist. They also gave a much more simplified formula for the S&T matrices, and they generalized it for arbitrary n's. They wrote down what the modular data should look like for arbitrary n, the modular data of the Drinfeld center. They noticed the modular data looks like there's some kind of squishing together of modular data of a finite group and a quantum group. And their paper was titled On the Exoticness of the Unrealizability of these Izumi-Hagrob categories. So they argued essentially that these shouldn't really be viewed as exotic at all. There's some infinite series. The modular data there should be some kind of construction relating quantum groups and finite groups, which gives you these. And they have a general form for the modular data. However, there's no general construction exists. So they only solved it for a few small groups. And it's not known whether their infinite series of S&T matrices actually are realized by categories or not. So they kind of argued that it should be, but again, at this point, only a few small examples are known to exist. Okay. So I'll finish up quite rapidly. So if you recall in the previously there were 2 exotic subfactors discovered. The first one is one of these. The Hagrob subfactor corresponds to the group Z3 in the Izumi-Hagrob series. The second one was a little bit more mysterious, so it wasn't really clear how that fit into the picture. So in recent work with Izumi and Noah Snyder, we found out that the Seda-Hagrob subfactor is also related to these type of quadratic categories, but it's more complicated. So it's related to the group Z4 cross Z2 in a non-obvious way. You have to take some orbifold and some Morita equivalents, and then you get. So the second exotic subfactor is also somehow related to this story of quadratic categories. moreover, we were able to write down a similar description of an infinite series of S and T matrices with Izumi for Z4n cross Z2. But at this point, only the first one is known to exist. We don't know if any of them exist beyond the first one coming from the Pythagorean subfactor. And finally, there's this third exotic subfactor called the extended Hague-Rupp subfactor. This one pretty clearly is not related to any of these quadratic categories, and no one really knows anything much about it. The modular data has been computed using combinatorial methods by Morrison and Gannon, but their method is quite different than Izumi's method. So their method doesn't really give an explicit description of the category. They sort of just figure out what the modular data has to be using combinatorial constraints. So the category is still quite mysterious, and it doesn't seem to belong to any family as far as anyone can tell. Okay. So let me just end with a few questions. So the more specific questions, which are maybe only of interest to practitioners in this area, are about existence of quadratic categories. So basically, the questions are, well, do these exist or not? So does there exist an Izumi Hague-Rupp series for these odd cyclic groups? Again, they seem to exist up to Z19, but there's no general construction known. Do they exist or not? No one really knows. What about for these new ones, the Z4n cross Z2? Do these exist? Again, only the first one is known in that case, but we have an infinite series of modular data. Evans-Gannon's work was for odd groups. Even groups are a little more complicated, so there's some ongoing work with Izumi in which we try to do the even group case. And there seems to be the parity of n. So 2n is the even number. The parity of n seems to come into play. Depending on whether n is odd or even, you get possibly multiple solutions. But again, there seems to be modular data, but only a few examples are known. The more general questions, which maybe have more interest to a wider audience, are the following. And I mentioned some of these during the talk. The first big question is, does every modular tensor category in fact come from conformal field theory? There are people who think this should be true. There's no real concrete evidence. But there are people who strongly feel it should be true, but it's not known how to construct a conformal field theory from a modular tensor category. So that's an open question. The second question is, do all modular tensor categories come from Drinfeld centers and quantum groups? So I mentioned all known examples seem to come from Drinfeld centers and quantum groups. The precise way of asking this question is that you can define a group called the Witt group, where the center of the Drinfeld center is supposed to be of something is supposed to be trivial in the Witt group, and then the question you would ask is the Witt group of modular tensor categories generated by quantum group representations? And again, some people conjecture this should be true. There's not really concrete evidence. The Witt group has been computed explicitly, but the proof is not really constructive. So they know what it has to be. It's some infinite direct sum of copies of Z and some torsion, but it's not really clear what the generators are. So it's not really known. And finally, the third question is one that motivates a lot of the work in subfactors, which is you have these exotic examples. So we do 3 exotic examples. 2 of them seem to be related to quadratic systems. There's a third one that doesn't seem to be related to anything. And then the question is, are there many more out there? Is this sort of unique? Maybe this really is related to something else. Or are there many sporadic examples all over the place, and we really have no idea? Terry Gannon, I think, is maybe optimistic about these existing. So he likes to give the analogy with finite groups. If you were classifying small finite groups, if you got up to all the groups up to order 5, you would think maybe all groups should be commutative, or you can make many silly conjectures if you only looked at the first few examples. And our knowledge at this point is very small. We looked at subfactors up to index 4 or 5. So we only see very few exotic examples, but maybe there's many more out there, maybe there's not. And this is a big philosophical question, I guess, or empirical question. All right, so I went a bit over, I guess. Thanks very much for your attention. This is Brazil and Australia, so I hope there'll be many more interactions between Australia and Brazil.